before I go to the next section or next topic, I would like to consider this example. So here we have two vectors v1 and v2, both are in R2. Vector v1 is 1 2 and vector v2 is 2 4. Now if you consider a linear combination of these two vectors, we have c1 v1 plus c2 v2. Now the question that we would like to ask is the following. So is there a linear combination that gives the zero vector in R2? Or in other words, can we find values for c1 and c2 that leads to the zero vector? Let's see. Zero vector in R2 is this. Of course, if c1 equals to 0 and c2 equals to 0, then your left hand side equals to the zero vector. But can we find any other values for c1 and c2 that gives the zero vector? The answer is yes. In this particular case, we have infinite many options. Here is one. Let's say c1 is negative 2 and c2 is 1. So then you will get negative 2 times vector 1 2 and 1 times vector 2 4, and as you can see, this linear combination will give you the zero vector. Okay, now, so in some sense, this vector v2 depends on vector v1. As you can see, 2 times vector v1 equals to v2. So even though I wrote two vectors here, actually one vector is redundant. In other words, these two vectors depend on one another. The next example I want to consider is this. Let's say vector v3 equals to 1 0 and vector v4 equals to 0 5. Now let's consider a linear combination of these two vectors that gives the zero vector. Okay, so we have c3 times vector 1 0 plus c4 times vector 0 5 equals to 0 0. So what are the c3 and c4 values that leads to the zero vector? Well, as you can see, if you want this first component equals to 0, then clearly the c3 value must be 0, and if you want the second component equals to 0, then c4 must be 0 as well. And that's the only way to get the zero vector from a linear combination of these two vectors. That's the only way. So mathematically, these two vectors are linearly independent. Okay, so now with this in mind, let's talk about linear dependence and general solutions. Now let's say we have vector valued functions, n number of vectors, and we say that these vectors are linearly dependent if we can find some non-zero constants such that this linear combination leads to the zero vector. So here you should pay attention to these three words, not all 0. Maybe you can have some c values where those c values equals to 0, but if you have linearly dependent vectors, definitely you can find c values with non-zero values. Otherwise they are linearly independent. So if all the c values equals to 0, then your vectors are linearly independent. Now in ODE 1 we used Wronskian to determine whether vectors are linearly independent or not. So this time we use the same concept, and here we have a theorem. This theorem says if we have n number of solution vectors x1, x2 up to xn, maybe these are functions of t. So we have n number of solutions for this homogeneous equation or homogeneous system x prime equals to ax. Then these solutions are linearly independent if and only if this Wronskian does not equals to 0. Now how do we define the Wronskian? Well, we calculate the determinant of a matrix. Now in this matrix, the first column, in this matrix our first column is the solution vector x1, the second column is the solution vector x2, and so on. And if you calculate this determinant, and if this determinant does not equals to 0 for all the t values, then your solution vectors are linearly independent. Your solution vectors are linearly independent. Now here is an example that we discussed earlier. Now in this particular problem I gave you the two solutions x1 and x2. Now if you want to check whether these two solution vectors are linearly independent or not, what you need to do is consider the Wronskian. So this first column contains the solution vector x1. That's why I have 3 e to the 2t and 2 e to the 2t. And then the second column contains the solution vector x2. Now let's calculate the determinant of this matrix. The determinant equals to this product, which is 9 times e to the 2t times e to the negative 5t minus 2 times e to the 2t times e to the negative 5t. E to the 2t times e to the negative 5t equals to e to the negative 3t. You have the same base, therefore we add the exponents. Then you will get minus 2 e to the negative 3t. This simplifies to 7 e to the negative 3t. Now as you can see, this value it will never become 0. Therefore we can say that our solution vectors are linearly independent. Now we defined from these solution sets we defined a set called fundamental set. So basically if we consider the general solution, then the general solution of a homogeneous problem contains the linear combination of these solution vectors. So basically if you have a homogeneous linear system with n dependent variables, then you should have n number of linearly independent solution vectors. Once we have those n number of solution vectors, you should consider a linear combination of those solution vectors to get the general solution. And here we denote the general solution using this X. And this is the fundamental solution set. Now, how do we know whether we have n linearly independent solutions or not? Well, we have this existence theorem of a fundamental set. So basically this theorem says if we have a homogeneous system, then there exists a fundamental solution set. So basically we have n number of linearly independent solution vectors. So this is the key point. Now, whenever we solve a homogeneous system of first order differential equations, let's say if we have n number of dependent variables, then we need to find n number of linearly independent solution vectors, and I denote those solution vectors using x1, x2 up to xn. With this